let's now prove corollary 158, which is a corollary to the amazing extension theorem. So we went over the statement of this result before, but we didn't go over the proof. And now we're ready for the proof. So this is about coming up with a nice description for the mu measurable sets. So let's suppose you have an algebra of sets and a non-negative measure, so countably additive non-negative function. So these are the hypotheses in which the amazing extension theorem applies and tells us that, you know, the outer measure is countably additive and blah, 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 blah. Then our corollary says a set is mu measurable if and only if the following happens. It's mu measurable if and only if you can stuff it in between two sets that are in the sigma algebra of sets generated by your original algebra. And you can do it in such a way that the outer measure of this complement is 0. So if it ended here, then you could object that this corollary is not so useful, since elements of the sigma algebra of sets generated by A are not so easy to describe. So this is not such a useful criterion. But there's more, which is that these don't need to be taken to be arbitrary elements from this sigma algebra. They can be taken to be certain kinds of elements that are easy to describe in a constructive way. So the inner one, A prime, can be taken from the collection of countable unions of countable intersections of things in the original algebra of sets. And A prime prime can be taken from the collection of countable intersections of countable unions of things from the original algebra of sets. All right, so let's get started proving this. So I've already got it set up here. So we're assuming I have an algebra of sets and mu a non-negative measure, just countably additive function. And this is an if and only if. So it's a criterion for mu measurability, right? It's an if and only if. So there'll be two directions. Assume B is mu measurable, and then I want to prove that this is possible. So assume B is mu measurable. Then I want to find A prime and A prime prime in the sigma algebra so that B is sandwiched between them, and the outer measure of this complement is 0. Now I'm going to use something from the amazing extension theorem to sort of rewrite the goal or re-express the goal. I'm going to pay attention to this, that the outer measure is countably additive on mu measurable sets. That includes sets in the sigma algebra generated by A, right? Because the sigma algebra generated by A is a subset of the collection of mu measurable sets because of this. So outer measure is countably additive on anything in this sigma algebra and is countably additive on any collection of mu measurable sets. Now, with that in mind, let me rewrite certain aspects of the goal. Let me just kind of talk through it and then rewrite the goal. So here, since mu star, the outer measure, is additive, since we have that from the amazing extension theorem, on things from here, which these are things from here, this can be written, this left-hand side is this difference, right? This happens whenever you have an additive function. So this thing can be written as the difference equals 0. So outer measure A prime prime equals outer measure A prime. And we also have monotonicity, right? So from here, we would have outer measure A prime less than or equal to outer measure B less than or equal to outer measure A prime prime. But these are equal in the context that I'm trying to put myself into. So if I achieve this, if I achieve my goal, then I will have achieved equality across the board here, right? And yeah, so this will give me a nice way of rewriting my goal. So let me re-express the goal. So by additivity, of mu star, which is a non-trivial fact that uses the that was worked out in the amazing extension theorem. Our goal is equivalent to the following. So our goal is now find A prime in the sigma algebra such that so like this with equality across the board. So what do we have to work with here? That B is mu measurable, right? That's what we have to work with. So somehow we need to use that. But it's really not so clear where it's going to end up being useful. So let's just keep in mind that, I mean, we already kind of used it to rewrite our goal. But let's just keep in mind that B is mu measurable, and then it's kind of interesting to see where that ends up being useful. We're actually going to start by doing stuff that has nothing to, that does not require mu measurability at all. So we're just going to use the outer measure. For each natural number n, do the following. If you take the outer measure of B, and so right now, again, this is something you can just do to any set B. It doesn't have to be mu measurable. If you add 1 over n to it, well, this is the infimum of something, right? The infimum of the collection of approximations from above of B. If I add 1 over n, then that's greater than the greatest lower bound, so it's not a lower bound. So there's something, so this is greater than the greatest lower bound. So there's some approximation from above of B which is less than, strictly less than this number, right? So an approximation from above, that comes from a countable family. Let's call it C M, running over natural numbers n, which covers B. So this is a countable family. This is a sequence, let's call it, in the original algebra of sets, such that it covers B. So that means B is contained in the union of all of these. And such that the series converges, the series of mu's of these guys converges to something less than, what it converges to would be what we call the approximation from above, and that converges to something less than this. So let me say that it converges and that it converges to something less than this in the same statement here. Okay, so now I'm doing this for each n, right? For each n. So let me put a decoration n on this. So for each n, there's going to be a cover coming from our algebra of sets that achieves this inequality with the 1 over n here. So these coverings kind of get tighter and tighter, you can imagine, I guess, as n gets larger and larger. Now, define so our purpose here is we're trying to build this A prime prime that sits above B, right? That contains B, and such that the outer measures are equal. Now this sum here is an upper bound on the outer measure of the union here, right? So the union here gets pretty close to doing what we want here. It's 1 over n close. And then what we're going to do is try to intersect over all n those things, which are all above b, and then that should work. So define dn, this is still for each n, we have this family, Cn, and define dn to be the union, to be this basically. Let me just copy that. Then notice that dn would be in the sigma algebra generated by A, right? Because it's a union of things in A. A countable union of things in A. And also, let's just record our observation that I talked through just now for later use. Mu star of dn, that's going to be mu star, the outer measure of this union, right? But outer measure is countably subadditive. Always, actually. Doesn't matter what sets you're applying it to. So we have this. And then that's less than mu star b plus 1 over n. So everything I'm doing so far still has not used the fact that b is mu measurable. This just would have worked for any set b that we're doing here. The only place where I used mu measurable for b is rewriting the goal from this to this. All right, so now dn almost achieves what I want, right? Mu star dn is almost to mu star b, but it's off by 1 over n. And as I increase n, that error gets better and better. So let a, which was it, a prime or a prime prime? A prime prime is the one from above. Let a prime prime be the intersection of all the dn's. Then think about mu star a prime prime. So it's mu star of the intersection of all the dn's. So that means it's mu star of something which is a subset of every single one of the dn's. So that means for all n, it's less than or equal to the outer measure of dn, right? So this is now, I'm saying for all n, this is less than or equal to that, which we just saw is less than outer measure b plus 1 over n. So this is bounded above by this for all n. For all n. Therefore, we have this, right? Since that's true for all n, for arbitrary n. You could say it's the order limit theorem, I guess, that we're using. Okay, but we also have the reverse inequality, obviously, because b is a subset of each one of these dn's, right? Let's put that observation here. By the way, b is a subset of dn. So b is a subset of the intersection of all of these dn's. So b is a subset of a prime prime. So that gives us the other inequality. And so we have equality. And look at that. We have not even actually used, so forget the goal for a second. If you just look at what we got using our b that we started with, we have not used the amazing extension theorem, and I think we have not even used the fact that b is mu measurable. So this is all stuff that you can do in general. That's kind of cool to see. So let's summarize. What did we do? we got basically this part. So we found A prime prime in the sigma algebra of sets generated by A, such that B is a subset of A prime prime, and the outer measures are equal. So that we did just for without using mu measurability of B, just with B just being any set. And by the way, in the statement of the corollary, we said A prime prime can be taken from the set of countable intersections of countable unions of things in A. Let's observe that our A prime prime is being taken from that. So A prime prime is the countable intersection of these D's, and each D is a countable union of C's, and the C's are all in A, right? So that's this statement. It's a countable intersection of D's. The D's are countable unions of C's, which are things in A. All right, now for the other part. Okay, so before moving on to try to get the A prime, let me summarize again what we just did, which I just said verbally, but I want to write it down. Given B subset of X, we know B is mu measurable, but we didn't need that. Just given any B subset of X, we were able to build an A prime prime, which was a countable intersection of countable unions of things in A, and which contained B as a subset, and which had the same outer measure as B. So I'm writing all that clearly because I'm now going to say do the same thing for the complement of B. So what do we get now? We get, I don't want to call it A prime since it's going to end up being, so I could give it a name like F or something, I don't know, but allow me to give it a name which is already the complement of something, because then I'm going to define A prime to be the complement of whatever I get out of this procedure. So we get, by doing the same for this, we get something whose complement I'm going to call A prime, so that this something can be called the complement of A prime, such that, first of all, this is a countable intersection of countable unions of things in A, and secondly, so I'm just copying this basically. Secondly, now I'm up here, when we did it for B, we got B as a subset of A prime prime. Here we're going to get the complement of B is a subset of the complement of A prime. And such that mu star outer measure complement B equals outer measure complement A prime. Okay, so now what do we know about A prime? Well, by De Morgan's law, applied a couple of times, A prime is the complement of something which is a countable intersection of countable unions of things in A. So A prime is a countable union of countable intersections of things in A. So that's part of what we wanted here, that it's a countable union of countable intersections of things in A. So that's good. Also, this inclusion of complements flips around and becomes this inclusion of sets. So A prime lives inside B. But what about this? So I will emphasize again, we have not used the amazing extension theorem yet, and we have not used the fact that B is mu measurable. B could have been an arbitrary set, except to re-express our goal, but we have not used it in any of our deductions so far. Now finally we're going to use it in order to rewrite this condition in terms of the complements of the complements, so in terms of B and A prime. So how about I do that in green, since that's the special moment where you see why this is a corollary to the amazing extension theorem, and where we use the fact that B is mu measurable. So the outer measure of B is the outer measure of the complement of B, nothing special yet, is the outer measure of X minus the outer measure of the complement of B. Now I'm using the countable additivity, actually just the finite additivity of mu star. That's built into the amazing extension theorem. The fact that mu star is additive and not merely subadditive. And then this equals that by the third bullet point up here. Oh, right, and in this step I'm also using the fact that B is mu measurable, right? Because I actually don't know that mu star is additive in general. I know that it's additive on mu measurable sets. So B is mu measurable, therefore also the complement of B is. X is always mu measurable. And now here I'm going to use the fact that A prime is mu measurable. And again, the additivity of outer measure on mu measurable sets. So here I get so these steps just don't work if you've got some random set B rather than a mu measurable set, and they don't work without already having a lot of the hard stuff from the amazing extension theorem. Okay, and finally we have mu star A. And you see, yeah, so mu star B equals mu star A prime is contained in B, and you see we reached this modified version of the goal. A prime contained in B, contained in A prime prime, and outer measure is equal across the board. And again, to see that this can be rewritten this way, I also used the additivity of mu star on A mu. So that's one direction. Let's now think about the other direction. So now suppose we have this criterion holding, and let's show that B is mu measurable. So suppose B is any old subset of X, and we've managed to sandwich it between two, oh, by the way, not just two random sets, but two things in there, such that the outer measure of this complement is 0, and then our goal is to show B is mu measurable. Well, if B is a subset of A prime, then B delete A prime is a subset of A prime prime delete A prime. Right, since B is a subset of A prime, this is a subset of that. So, well, outer measure is monotonic, so outer measure of this is less than or equal to outer measure of that, which is hypothesized to be 0 here. Outer measure is non-negative, so outer measure of this is 0, right? But if the outer measure of something is 0, then it's sort of automatically mu measurable, because you're saying the outer measure of its symmetric difference from the empty set is 0, right? The symmetric difference from the empty set is just itself, right? If you take this and symmetric difference of the empty set, you just get this. So you're saying that that's 0, and that's going to be less than any positive epsilon you might come up with. And this here is an element of the algebra of sets. So this is meeting the definition of mu measurability, right? There exists, for any positive epsilon, there exists something. Just use the empty set, so that when you symmetric difference, the outer measure is less than that epsilon. So that's telling us that this is mu measurable. And we already know we already know A prime is mu measurable. Why? Because A prime is in the sigma algebra generated by A, and that's a subset of the collection of mu measurable sets. That was another one of our conclusions from the amazing extension theorem. So this is, you could view this as, you could view B as first taking A prime, taking B without the parts that are in A prime, and then unioning in the parts that are in A prime. And so B appears to be a union of two things that are both mu measurable. A prime is mu measurable because it's in the sigma algebra generated by A, and this is mu measurable because we just showed it was. So a union of two mu measurables is mu measurable because, again, one of our conclusions in our amazing extension theorem was that this is, well, we showed it's a sigma algebra, but here we just need that it's an algebra of sets. It's closed-number unions. All right, that direction was a little bit easier, I think. So that's it for Corollary 158.